pretty much taken. There's some room up here if you want to just grab a wall or some floor. Thanks for coming out to Truly tonight. My name is Todd Holloway. I'm the data science lead here. Tonight it's also sponsored by Budweiser. We have lots of beer in the back, so feel free during the talk to help yourself. The only thing you need to know tonight, other than the speaker, is the talk will last until about 8:15, and the doors will stay open until about 8:30, 8:45. And so there'll be some time left over afterwards to drink more and network and so on. And if you guys want to hang around even longer, there's usually folks who wander out down to the bars on Mina Street. So the only other cool thing happening is we hit 6,000 members today. That's very cool. So tonight's speaker is Brad Null. Brad managed to earn a PhD in baseball optimization from Stanford. That's very cool. And he is also the chief scientist at Reputation.com and founder of BracketVoodoo.com. And a generally very interesting guy. So I'm looking forward to this talk. So let's welcome Brad.
Thanks, Todd. All right, so Todd invited me to come out here. First of all, thanks everyone for coming out. And he thought it would be interesting to you guys to hear basically about some of the research I've done in sports analytics over the last. We good for sound? My position center. Close. Oh, no, I'm looking. Anyway, so as Todd said, I did my PhD at Stanford, actually in operations research, and I did my thesis on stochastic modeling and optimization in baseball. So I thought it would be interesting to louder. Is that better? Okay. All right. I'm gonna be eating this thing all night. Anyway, I thought it would be interesting to start. One more. All right, we're back. So in any case, I thought it would be interesting to start the talk basically from the origins of how I got into sports analytics in the first place during my, around when I started my PhD studies in 2003, 2004. And actually that was around the time there were actually a couple of publications that had a lot to do with motivating me to get started in sports analytics. The first one, I'm sure just about all of you guys are familiar with, is the book Moneyball, the bestseller in 2004 by Michael Lewis. And the basic thesis of this book, obviously, as most of you know, I'm sure, is that the A's are using analysis to play smarter and win games. It's a very well-written book, very popular book, even more popular movie starring Brad Pitt, obviously. But they do cover some of the analytics that the A's were supposedly using to help them win. And some of the sample insights there were don't find, don't steal, sign players with a high on-base percentage. And about the same time, there's another little bit lesser-known publication, a paper by an economist from Berkeley, David Romer, that came out, I think, first in 2003, called It's Fourth Down and What Does Bellman's Equation Say? And so basically, Professor Romer had set up a classical dynamic program to analyze the game of football, and in particular to analyze when it was optimal for teams to go for it on fourth down. And he basically concluded that teams are a little too, by far too conservative on fourth down. They should be going for it a lot more often rather than punting and kicking as much as they do. And this paper was potentially more influential in me getting involved in sports analytics, in part because I was first exposed to this paper, not in some academic journal or whatnot, but actually I saw a feature on it on SportsCenter, not necessarily presented by this guy, but when I was exposed to this paper, they were actually doing a feature on this paper that this guy had written about when to go for it on fourth down. And actually, they'd gotten a lot of football coaches to comment on what this guy was concluding. Most of them weren't, very positive or complimentary of his research, but nonetheless, there was a strong response. A lot of people were responding to that paper, and that was interesting to me. And that's kind of the first way that both of these write-ups motivated me, was that they had a strong response. Obviously, Moneyball has had a very significant impact, had an impact before it was written in terms of what the A's were doing. And since then, it's had a very significant impact across baseball, across sports, some would argue across other industries. And the second reason, obviously, these papers were interesting to me was that there were very compelling insights. That people were doing analysis and coming up with compelling insight for how you could actually do the sort of operations research that I was working on and help make better decisions on when to bunt, when to steal, when to go for it on fourth down. Further, these were, like I said, classical techniques that I was familiar with, that I was studying. And finally, I saw, when I looked at them, when I looked at the papers, that there was room for improvement. In my mind, at least, there was a way to enhance the models and try to get deeper insights. So that's what I decided to do when I first got into sports analytics, was take some of this research and try to enhance the models, build deeper models, and see if we could, at least as a first proof of concept, get some deeper insights with respect to these problems. So that's what I did. So the first thing I wanted to do with respect to the analysis that was underlying these papers was change the objective function. Romer's paper about football was actually trying to evaluate fourth down decisions by evaluating whether teams were actually maximizing the number of points they were going to score on that drive, net of whatever the value of the field position they were leaving for the other team. And all of the dynamic programs that were mentioned in Moneyball, they were all trying to maximize the number of runs scored in a half an inning, as opposed to another reasonable objective function, a more reasonable objective function of maximizing the probability of winning a game. And it was actually Richard Bellman himself, the father of dynamic programming, who wrote one of these early papers on dynamic programming and optimization in baseball, who hypothesized in the 70s that using this objective function of maximizing the number of runs was a good proxy for maximizing the probability of a team winning a game. So I wanted to test that hypothesis. So how do you do that? It's actually relatively straightforward. We just extend the dynamic program. So the models that these guys were building, for instance, for baseball, to model half an inning, they maybe had tens or hundreds of states accounting for where the base runners were at, how many outs there were in the inning, and potentially where we were at in the lineup. So we just extend that. We also keep track of what inning we're at, what half inning we're in, where the other team is at in the lineup, and what the score differential is. So now we've just taken this 30 or 300 state dynamic program, and we've made it a little bit bigger. It's about, the model we were using had about 800,000 states. But hey, this was the 21st century. That actually wasn't a problem for us. Maybe it was a problem for Bellman, but it wasn't for us. And then we wanted to evaluate in different contexts. Also, all the analyses that are mentioned in these write-ups was based on average case analysis. All the transition probabilities they were using was from average stats compiled over an entire league for a number of seasons. We're like, well, maybe on average it's not optimal to bunt, but what about for a specific game, for a specific player in a specific situation, a specific inning? Maybe it is. So we wanted to look into that as well. So then we just had to take those average transition probabilities and come up with transition probabilities that corresponded to specific teams and specific players. And at that point, for the initial analysis we were doing, we actually started with, I would call them lazy transition probabilities. So we just really extended the model by looking at historical stats for the players in the games we were looking at. And just, for instance, with respect to the batters in a game, the historical batting stats, the one-sided stats, only looking at the batter, not the pitcher, and just analyzed the problem that way to see, if we were getting different results from the canonical papers. And so we set that up, we did that pretty quickly, and we actually got some interesting results. So the first thing I actually wanted to look at with respect to baseball was the decision of whether or not to intentionally walk the batter. And in part I wanted to do this because I wanted to focus on a game between the Giants and the Dodgers in 2004, and I wanted to look at specifically when to intentionally walk Barry Bonds. As many of you probably remember, 2004, Barry Bonds was at the height of his possibly chemically induced powers. But he was at that point in time, easily the best player in baseball and possibly the best player in the history of baseball at any point in time. And he was actually being walked at a historic rate, intentionally and otherwise. So there was a lot of discussion about when it was optimal to intentionally walk Bonds. So I wanted to set up this problem and see. And for one thing, I wanted to analyze, well, what if we use this objective function for the Dodgers of minimizing the number of runs the Giants would score in any half inning, and compare that with what if we use the objective function of minimizing the Giants' probability of winning the game. And the first thing we noticed kind of immediately was actually, just looking at the first inning of the game with these two objective functions, we see very different, optimal strategies. For instance, when we're trying to minimize the Giants' number of runs scored, the model's telling us to walk Bonds, just about any time the first base is open, or at least when there's just a man on second or just a man on third. When we want to minimize the Giants' win probability, the model's telling us to never walk Bonds in the first inning. So this was interesting, so we wanted to dig a little deeper and understand why this was. And the primary reason certainly seems to be that, obviously the primary difference is we have a new model that's capturing a lot more nuance in the game. And specifically, it's capturing this ripple effect of, well, what happens after the end of the first inning? So with respect to these two decisions, for instance, if Bonds comes up in the first inning with 2 outs and you pitch to him and you get him out, then you're starting in, you could look at it as starting an 8-inning game and Bonds is batting 9th. On the contrary, if you walk him, pitch to the next guy, get the next guy out, then you've got this 8-inning game and Bonds is batting 8th. And in just about any scenario, the Giants are going to do better. They're going to, in the sense of scoring more runs, they're going to score more runs on average in that 8-inning game where he's batting 8th versus where he's batting 9th. So that's a factor certainly weighing things in favor of pitching to Bonds, hoping you can get him out and be left with a better scenario after the fact. And it turns out, at least in this case, that factor and the associated factors are actually overweighting how much benefit we get by minimizing the number of runs that the Giants would score in that first inning alone. And the optimal policy with respect to trying to minimize the Giants' probability of winning the game was to never walk Bonds in the first inning, go after him in the first inning. And so that was, just a longer way of saying that the objective function matters. That actually modeling out this more complex model is giving us greater insight into the problem. We also looked at, some of these other decisions. In particular, we looked at analyzing, when it was optimal for teams to bunt, and not just sacrifice bunt, but bunt in general for all American League games over the course of a particular season, throwing out the National League, given the propensity for pitchers to bunt in that league. Now, here again, using transition probabilities derived from the players in those lineups. And we found that actually when we looked at this with respect to the different game, the optimal frequency of teams to bunt from game to game varied by up to a multiple of 3x. Further, we actually found that in our analysis, it was optimal for teams to attempt to bunt a lot more than maybe this sabermetric conventional wisdom that was out there. But that's another point that I'm going to leave for another discussion. But more importantly to what we were trying to figure out with this proof of concept was that the context matters. Looking at the different probabilities for different teams came up with very different strategies, which had very different impact in the underlying probability for the teams to win the game. I should say, if you guys have any questions or anything to add, feel free to, to speak up at any time. Happy to take questions. And so we analyzed a similar model with respect to football, analyzing optimal 4th down decisions for specific games, and actually modeling out the whole game rather than one drive. And we saw a similar sort of phenomenon looking at optimal strategy on 4th downs in the first quarter to the second quarter and seeing that they're changing, effectively giving us insight that this maximizing the net expected number of points for a team in a certain drive doesn't hold as a good proxy, at least over the first half of the game. So just more insight that actually building that deeper model was actually giving us more nuanced, optimal strategies. But we're still concluding that teams should go for it a lot more often than they actually were, as Romer was. So, which just as a side point, led us to realize, well, maybe even this objective function of maximizing your probability of winning the game isn't still, the right objective function. In fact, it's a common phenomenon in various fields, various industries that people, that employees tend to hew towards, conventional wisdom. They tend to do what's kind of expected of them to do. They take a low-risk approach, and the economist's point of view is that, well, there's another objective that these people are trying to optimize with respect to, and it's maximize the probability of keeping your job. And this is certainly something, as I've said, a phenomenon that we see all over, not just in sports, but maybe there's even more motivation for this among coaches in sports, because as opposed to you and I, who might have pressure to do whatever anyone else would expect you to do. The coaches are actually, much more open to public scrutiny. Everyone is kind of invited to see what they're doing and analyze what they're doing. And also, there's a very high variance of actual outcomes. I mean, consider a football coach who he could follow the conventional wisdom, and he might have a 50-50 chance of winning a game, and in that 50% chance that he loses the game, nobody's going to give him any crap about it because that's what everyone else would have done. Or he could do the quote-unquote optimal thing, and now he's got a 51% chance of winning the game, but there's a 49% chance it doesn't play out, and then everyone's chewing him out, telling him he's an idiot. So, looked at it in that lens, obviously, maybe there's a little bit more going on there. Which is not to say that that's necessarily the reason that all the coaches are deciding, not to go for it in these various scenarios. I certainly believe that many of them still believe what they're doing is maximizing their chance of winning the game, but kind of cutting it out there. But even if you did convince them that, hey, maybe it's slightly better to go for it, there's still going to be that pressure. They're really going to need to see, some clear, compelling evidence that this is a much better opportunity, because they're going to need to be able to defend themselves down the line. That's just going to be a factor of how they're making their decisions. So we did that analysis, and to my mind, that was a good proof of concept that building these better models, we get bigger insights. But we're still just, in my mind, generating rules of thumb and generalized insights. Really, by virtue of these lazy transition probabilities, you couldn't be confident that the optimal strategies that we're generating with respect to a specific game are truly, optimal for that particular game. And that's what I really wanted. That's what I decided, going back to the chronology of where I was and why I was doing this. That's what I decided at that point to focus on with respect to my, PhD thesis and dissertation was, well, let's actually build out this stochastic system. Let's actually try to have this defensible model that can generate these, solid game-specific insights, or at the very least be able to, defensively second-guess the coaches if we wanted to use the model for that purpose. So that's what I did, and that's really the first time that I was kind of confronted with what I see as the hardest job in applied operations research, which is not formulating the problem or modeling the problem or solving the system, but being able to accurately assess the parameters of the optimization problem you're working with. Because if you're working with just kind of arbitrary parameters that you threw together, especially these stochastic problems with these transition probabilities, then it's just another case of garbage in, garbage out. So that's really what I see as my introduction to data science. This new problem where I wanted to use data to really get a reliable prediction of play outcomes for any plate appearance in any baseball game, which I was going to then use to incorporate into this model of the game. So the main challenges then, as I saw them at that point in time, were we're still doing this one-sided estimation of player ability. So we still need to model the batter versus the pitcher, versus whatever other environmental impacts might affect the plate appearance. And we also have this other problem of, if we want to use historical data, well, a lot of the players have minimal data or no data. They just came up. So we have this kind of classical cold start problem. And at the same time, for all the players that do have data, we've got this regression to the mean, which I'm sure most of you guys aren't familiar with, but are familiar with. But just to review them, just to make it clear in this context, what you see in baseball is you see in a lot of other contexts. The best players from one year tend to, quote unquote, revert towards mediocrity or regress towards the mean. They tend to not do as well the next year. And it's a common phenomenon, and you see this in all sorts of applications. And that's precisely because this extreme performance is a function of both superior ability on average of those players, but also luck. The ones that are doing the very best are also getting a little bit lucky. When we look at it from year to year, from game to game, from any period to any subsequent period, then the superior ability may tend to persist, but the luck is generally not going to repeat itself, and that's where the regression to the mean comes from. And all of this, looking at this, understanding of this, leads to led me to the obvious conclusion. Well, then we need a player ability model. We need to model what that underlying ability is, so we can remove the luck, so we can accurately shrink our estimates using this data. So we set about to build that player ability model. Is everybody hearing me? We're good? You keeping up? All right. It's hot up here. So we decided to build that model, especially in light of kind of the primary application we had for it of incorporating into these transition probabilities of the baseball game. So we came up with 14 possible outcomes for any plate appearance in baseball. We decided to model abilities for every player with respect to those 14 possible outcomes. So for instance, every player had an ability of his underlying true likelihood of generating a walk under normal circumstances, or striking out, or getting hit by a pitch, or hitting a home run, or hitting a ground ball single. I'll actually show you the abilities in a minute, but to avoid repeating myself, you get the gist. 14 possible things that could happen whenever there's any at-bat or any plate appearance. So then, we assume, in the model's sake, that every player has some true underlying ability with respect to each of these 14 abilities, and those true underlying abilities are drawn from prior distribution. Then, given the player's evidence, or in this case, the historical data with respect to that batter or pitcher, we can update the prior, get a posterior distribution for that player, and then, if we want, pull a point estimate from that distribution. And so this model we're actually looking at, these abilities are actually, this is a multinomial model we want to generate, with 14 possible outcomes, disjoint outcomes from any plate appearance. So the most common, obvious first model to try to generate a prior distribution is the Dirichlet distribution, which is the most common prior distribution used in conjunction with multinomial data, and it's precisely the most common prior because it's conjugate prior to multinomial data, which means that when you take the prior, you update the prior with evidence, you get the posterior distribution. The posterior is still Dirichlet, for those of you who are familiar with conjugate prior. And it's the multinomial equivalent of the beta, of what the beta distribution is for the binomial, since I'm sure a lot of you guys are more familiar with that than with the Dirichlet. So just a quick example of kind of a Dirichlet, or actually a beta distribution in practice. So let's say, for instance, that this solid line here represents the prior distribution for all batters according to some ability. Let's say it's walk rate, or their ability to generate a walk in any at-bat. It's a little too far to the right for that, but let's just say it is. This is actually a beta curve with parameters 10 and 40. The mean of this is 20%. Now then, let's say we observe some batter who bats 200 times, he strikes out 60 times, or he walks 60 times, he doesn't walk the other 140 times. In this case, using a Dirichlet multinomial model, you would just get the posterior for that player by adding the prior parameters to the evidence. So that 10 plus 60 equals 70, that 40 plus 140 equals 180, and that's what the posterior distribution would be for that batter. So obviously, very simple. It's very obvious why this is a very appealing way to do priors and posteriors for this kind of data. Okay. But we actually, in the course of setting up this model, evaluating how well it fit, running a battery of diagnostics analyses or whatnot, came up with a few ways that we wanted to extend that model. And this, took us a lot more time than the 3 minutes I'm going to take describing it to you, but obviously we're condensing time here. So the first thing we did was we took that Dirichlet and replaced it with a nested Dirichlet function, which essentially modifies the Dirichlet by adding a series of nesting variables, such that for each of the 14 event types, they're actually modeled as occurring according to a tree. First, we figure out, does the batter walk or not walk? If he doesn't walk, then there's this conditional tree underneath that. And all these things are built out according to a tree, and in that tree, every level of that tree is a conditionally independent beta distribution. And the primary reason we did that was because the Dirichlet actually has a very limiting covariance matrix of the relationship between those 14 underlying abilities. For one thing, the marginals, they all have to be negatively correlated with each other. There's also this strict variance relationship of how the mean and variance of any one of those abilities has to be related. So being able to turn this into a tree actually helped us with that, which was a limiting problem for us, because, for instance, we know from looking at historical data that the strikeout rates and the walk rates of batters are positively correlated, historically, and also the walk rate of batters versus the ground ball single rate of batters. Batters tend to have a much wider dispersion of underlying walk abilities than they do of being able to influence whether they hit a ground ball single. So we wanted a more flexible model to help us deal with that. And at the same time, this nested model is still conjugate to multinomial evidence, so we weren't giving that up either. And so after we put that in and we continued to analyze and decide what we needed to do with this model, we also needed to add a couple of factors that allowed for these underlying abilities to change over time. And the first effect we wanted to add was a deterministic effect, which is basically related to aging. Over time, as a player gets older, there are very predictable ways that players tend to perform better or worse with respect to different abilities as time travels. So we added in a deterministic effect, which we used the data to help us estimate. And we added that in on the ability level for each of those abilities at each of the subsequent conditional nodes in the tree. But then beyond that, we also noticed that still after introducing this prior distribution, introducing this age effects, we still got some kind of over dispersion in the data. And so we're seeing evidence that there were actually these other non-deterministic effects. The player abilities were still changing over time in other random and unpredictable ways, beyond what we could explain with the uncertainty related to the prior and posterior distributions, beyond what we could explain with the age effects. So we added these non-deterministic, the stochastic process of how abilities changed over time as well. Then we used maximum likelihood to basically simultaneously help us fit this whole model. So what it had to do essentially was it had to tell us what the best nesting tree is. We didn't know a priori what that tree was, so we essentially just compared a lot of possible trees. We took a lot of possible trees. We found the best nested beta parameter, prior parameters with respect to that tree using maximum likelihood. We identified the optimal deterministic and non-deterministic time varying parameters, and we fit all this all simultaneously to get the maximum likelihood best tree with the nested beta distributions and the other time varying parameters as well. And so this is what our nested Dirichlet tree looks like for baseball abilities. So quickly, these are the 14 abilities. We've got catcher's interference at the top, hit by pitch. Any of you guys that are familiar with Craig Biggio will know that being able to get hit by a pitch is in fact a batter ability. Fly ball, and then underneath fly ball, we actually have nested the possible outcomes of a fly ball, out, single, double, triple, home run, ground ball, and those 5 outcomes, and then walks and strikeouts here at the end. And now, obviously, some of these things in here are very rare events: catcher's interference, ground ball, home run, and you could argue, fairly that we could just throw those out and the model would be fine, and that's true. But we kind of we identified the 14 abilities right from the beginning, and then it was more trouble than it was worth to remove them. Yes.
Does the meaning of the tree imply that somehow the events above help in some small way determine the events below? In other words, the propensity to hit fly balls versus ground. I guess I'm curious by the thing about ground balls versus strikeouts and walks.
Mm-hmm.
Why is the strikeout versus walk thing in that part of the tree?
Well, that's actually my next point.
Oh.
So, basically, the way this works, the way the nested Dirichlet tree works, is that, as I mentioned, strikeouts and walks tend to be positively correlated, and this is how you actually tend to end up with positively correlated events in a nested tree like this. So that's fundamentally, why they're there. Looking at the data, they're there just, that's what maximum likelihood told us to do, but also it is matching that correlation. And that was kind of one of the first insight out of this model too. I'm sorry, did you have a question also? No? Someone over there raised their hand? No? You have a question.
Reason why you decided to exclude line drives and just ground balls and ground balls?
That's a function of the data I had available. So the question was, so the first question actually I should have repeated was why are walks and strikeouts at the bottom, and the best reasoning behind it is obviously that those are positively correlated, and that's how they get correlated. The second question was, why did you exclude line drives from your event space? And that's more than anything a function of the data I had available. I had somewhat reliable data over the period I was looking at, pretty much from 2003 to the present, of whether any historical plate appearance was a fly ball or ground ball, but I didn't have very reliable data of whether it was a line drive at that point. Yeah.
Exactly. That's if you're looking at public data sets, whether something gets coded as a line drive versus a fly ball is subject to all kinds of biases and irregularities. It's either in the air or on the ground.
And I'll talk about, briefly at the end, the tracking data that's starting to come about over the last couple of years, and how, hopefully, for all you guys, as you get serious with this sort of analysis in 2 or 3 years, you won't have to worry about that, because you'll know exactly where every ball was hit, at what velocity, at what angle, etc. You'll be able to build much cooler models than this. When we started doing this, this was really the best data. This was the most granular data we had. Any more questions?
What was it the numbers represent at the top of the tree, or at each node?
So the numbers here just represent additional variables. So a Dirichlet distribution for these 14 events would have 14 parameters. The nested Dirichlet actually now has 26 parameters, and that's me basically identifying what the 26 parameters are. That's all that means. Yeah.
I'm sorry, just one more comment.
Sure.
You're right that there's actually being data collected that we basically quote perfect in theory, but according to the my people I've talked to in the field, the teams are going to keep it to themselves and never be released to the public in the foreseeable future.
Right. Yeah. So your point was this new hit FX data, the field FX data. I'll talk about a little bit more. I mean, there's still most of that stuff's not in the public. The pitch FX data, we have access to, and that's actually a really rich data set in itself. But yeah, the data that's being gathered in terms of exact, which I think you were kind of raising the point. We don't even know how exact it is either. But that's still not available to the public either. So that's another problem to figure out down the road too. Any more questions? By all means.
All right. Well,
yeah.
The strike and the strikeout and the walk. Is that like how big is not swinging on a 3-2 count influencing that? If you remove that, does that diminish significantly, or if the batter doesn't swing on a 3-2 count, if you remove all those events, how do they stay correlated?
That's a good question. I actually haven't analyzed that. But I think those are correlated precisely because those are the batters that tend to go deeper. They tend to swing and miss more. They tend to take more pitches, go deeper in the count. So that and various related phenomena could kind of swing things. And it's certainly a very interesting consideration if you're going to. Another kind of advancement, that I was going to mention later is, obviously taking this analysis from the play level to the pitch level, there's certainly a lot more things you can do with it that, modeling those dynamics that we don't have in this model right now. Yeah.
When you were talking about determined factors, do you like getting traded to another team or playing in a bigger ballpark count?
Yes. Yeah. There are a lot of other factors, these environmental factors that impact, player ability, impact the output of plays, the stadium you're playing in, who has home field advantage, et cetera, et cetera. I was planning to mostly not mention those today, just because, for the sake of time, we can talk all day, we can talk all night if you want. But yeah, obviously, the park you play in, who has home field advantage, all those factors we do take into account, within the models, and actually. Within these models, updating this data, we do in fact actually, for the models that we're actually using in practice, transform that data. So if we look at a player from the Colorado Rockies and look at how many home runs, fly ball home runs he hits versus fly ball outs, we'll modify that using park factors. We'll kind of normalize that data that we're actually sucking into in terms of what that person actually did last year. But for the sake of this talk, I was kind of glossing over that, but no, that's a very significant point. So a few insights then with respect to this model. The first one was, so this process we built, we came up with this new way to condition the outcomes, to build a tree that helped us kind of condition, well, if first let's look at if the player does this or that or the other, and as we mentioned, we put walks and strikeouts at the bottom precisely because those are positively correlated. Well, the model dictated that, the analysis dictated that, but they're down there because they're positively correlated. That gives us a stronger model. Other people had actually manually curated models of conditioning outcomes in a plate appearance, and all the models to this time were actually flipped around. They would say, well, first let's see if they walk the batter. Then let's see if the batter strikes out. And then if he hits the ball, let's see if it's a home run. And then let's model the distribution of all the other events. And that seemed intuitive at the time, but our analysis told us, well, let's actually flip the model. And the more I've looked at it since we built this model, this actually makes a lot more sense to me, because if you're thinking about the process of events, really, first what happens is, do you hit the ball? And if you don't hit the ball, if you go through all your pitches, then it's, do you walk or strike out? So this tree actually makes a lot more sense, but yet that wasn't really, generally how people were looking at it until this time. Also, the model, the output of the model, showed us that there was evidence that pitchers, do have an impact on balls in play. And more than that, we have a model that measures that impact. And this was significant because, around the same time, other people were doing research and theorizing that, well, pitchers don't actually impact balls in play at all. All the pitchers impact is whether it's a walk, whether it's a strikeout, whether it's a home run. And balls in play are generally random, or whatever effects are mostly attributable to the fielders. And those and there were models being built that were basically ignoring this completely. Since then, that's those models have changed a bit. But at the time, and it was an important realization, I think, that well, pitchers do have the most impact on whether the batter walks or strikes out. But then it was a simplification in those sorts of models to throw out the other impacts. But now we have a way that we can actually account for all of that and ascribe via the way we're nesting this in the parameters, the different prior distributions we have at each level. We're able to weight all the abilities in a fair and reasonable way. Also, our model, especially by virtue of these the stochastic process that underlies abilities, give us evidence that the players do get hot. We generated evidence from the conclusions we were drawing that players' abilities do change over time in non-deterministic ways. And this is interesting because actually a lot of people still are performing a lot of studies, and the majority of the studies on whether there's such a thing as a hot hand in baseball or basketball have concluded that either no, there's no such thing, or we can't find one. But our model actually, does find that. It finds that players, seem to go through periods where they're performing better and worse. And also, our model, concluded that this time varying effects are somewhat mean reverting. That when players get hot, they tend to cool down. They tend to go back to some long run actually towards the population mean. And finally, when we analyzed these models and we looked at how predictive they were at various levels, at the play level, at the season level, we found that the point estimates that came out of these player posterior distributions after a season were actually very good predictors of the subsequent year's performance. As good or better than any other publicly available models that were predicting how good players would do from year to year. So, I don't think those are all interesting. Other useful features of the model, we can use it in our Markov chain, which is good. That's the first and foremost reason we built it. It's easy to update. It's still conjugate prior. The way we added all those factors, we still managed to keep it, a conjugate prior model. And the way we incorporated, the reason we incorporated, these various parameters of prior and then the stochastic process, the deviation over time, it allows us, the model is accurately measuring uncertainty, or it's fitting our measures of uncertainty of player abilities from day to day, from season to season. This is important because, generally, especially, among heuristic methods that are trying to forecast or project things, if you look at, for instance, Yahoo Fantasy's projections of how your fantasy football team's going to do next week, you'll see that they're, a lot of heuristic methods are grossly over or underweighting new information. They're either applying too much weight to last week, yesterday this guy hit 2 home runs, or they've got some very crude method of, we weight the last, we just look at the last 30-day moving average or whatever it is. But we actually have a model that's telling us, exactly how to weight all the new information, and it's telling us the different weights for each of the different ability types, and it seems to be doing that well. And finally, this is actually, in my experience, over the last 10 years, been a very generalizable model, both the nested Dirichlet priors and the related stochastic processes for dealing with population priors and how abilities of players and entities move over time. And I've actually used it to apply to several other problems, both evaluating other sports players and teams' abilities, or with respect to research I've done in ads and web analysis, evaluating kind of the performance of online advertisements, what different entities will be rated on review sites, the popularity of web pages, and then various other types of study. For instance, we've also done some work in analyzing resumes and the impacts of schools and fields of studies and degrees people had to kind of impact what their career trajectory looked like, and we use some of the models to model kind of the distribution of impacts for schools, fields of studies, and such. So I've at least found that it's come in useful in a lot of applications. It's actually been very generalized. So we had this great model of player ability, and then we have to go back and throw it. Now we have to look at the batters and the pitchers, and we have to fit them together and figure out, well, what is this transition probability we can plug back into the dynamic programming. So for the sake of time, I'm not really going to talk about this at all, but rest assured that there are methods out there. The log5, the odds ratio method, by far the most popular method in kind of the sabermetric literature. Also, logistic regression, various other methods we can apply to come up with this probability, incorporate these other significant factors, park factor, like you mentioned, home field advantage, platoon effects, if the batter's right-handed, the pitcher's left-handed, et cetera, varying degrees of complexity, and various ways that people go about kind of merging the batter and the pitcher estimates and getting that estimate of what's going to happen in any plate appearance. And this takes us back to our model of an entire game. So now we have these transition probabilities. We want to look at a model of the game. There's still, in terms of building out this this kind of complex system, a few other things we threw in. Most importantly, perhaps kind of trying to get a good strategy heuristic, especially to approximate how different coaches are going to use their bullpen and other decisions they're going to make. That's also not an easy problem, but nonetheless one I'm just decided not to spend any time on today. But yada yada yada, proof presto, then we have this quote unquote good model of a baseball game. And by good, one benchmark we were using was looking at the implied probabilities from gambling lines, and then our forecasts for these games are actually, we got to the point where they're basically on par. They're as good, providing as much information as the gambling lines. And that was an important kind of benchmark to me, and that combined with kind of the other analyses, making sure we removed the bias, took into account what seemed to be all the reasonable factors, gave us much more confidence then in these evaluations of strategic decisions within games, the bunting, the stealing, the intentional walking, and even evaluating decisions about substitutions, optimal lineups, and various other decisions. So then, after all that, after starting with just wanting to make some minor tweaks to some models we read about Moneyball, 3 years later we had this system. We built out these models of player ability. We can predict how estimate how good players are. Then we can estimate what's going to happen in any plate appearance. We throw that into a model of the game. We estimate the win probability for any team at any point in the game. And then using that, evaluate kind of in-game optimization. And then we can take it further, model an entire season, look at distribution of season outcomes, your probability of winning the pennant, et cetera, and then other long-term analysis related to that. So with respect to that system, just to reiterate a few things I kind of mentioned. So we don't just have good predictions of who's going to win the game, online with the betting lines, but we also have very advanced predictions of who's going to win the game at any point in time. And we don't just have a good point estimate of player abilities, but we have a good forecast of player stats over any time frame, with respect to any stat, and we can get kind of a full distribution of the likelihood of different outcomes for different players. And then with respect to these larger scale, these decision problems we want to look at over the course of seasons or careers, now we can take this and we can evaluate, player valuation. We can evaluate player acquisition, trades, drafts, et cetera. And in particular, we can evaluate, since we have this posterior distribution of a player, we have some concept of how much uncertainty we have with respect to that player. We can view that player as a real option. That upside, every player has, they have upside, they have downside that corresponds to them. We can see, well, what's that worth? And so we can evaluate even kind of exploitation trade-off type problems with respect to optimally experimenting with new call-ups and how much, what's the optimal time to give them to learn the right amount about them before we can send them back to the minors. Or evaluate, well, there's some value of this uncertainty, this upside with respect to your team's performance over the season. It actually, whatever that point estimate was of the number of wins you're going to get, adding more uncertainty with respect to players, more upside, but that gives you more upside, more variance with respect to how many wins you're going to get. And so the optimal, because the optimal objective function over the course of the season isn't maximizing the expected number of wins, it's more maximizing the probability you're going to win the World Series or win the Super Bowl. So then we can do that analysis as well. We did, still, a test case there, looking at teams, looking at some of the veterans on teams that we felt like we had a good feel for how good they were. What would happen if we replaced them with rookies with comparable expected ability, but with a little more uncertainty? We actually saw in these analyses that would increase the probability of these making the playoffs by 20% or more, which is not to say from 10 to 30%, more to say from 3 to 3.6%. But still, significant. So, one more benefit I wanted to talk about before I kind of, started talking about things other than the system was, so in complex systems like the game of baseball, as I'm sure a lot of you guys know, it can be hard to parse out the impact of one variable from the multitude of others. If you do a marginal analysis without accounting, for everything else going on, it's hard to really see what impact that variable is having. Sure, I'm preaching to the choir, versus how it's correlated with other events, and that's kind of what we saw with respect to some of the previous research that have been done on whether there was such a thing as a hot hand, how much the pitcher impacts balls in play. But we've seen that a lot of other times in terms of it's hard to really identify platoon effects or age effects because there's other bias going on. And so, in my experience, the more with these sorts of models we can control for all these other variables that might also be impacting our results, then the deeper insights we can get with respect to whatever the new marginal variable we're looking at there is. And it certainly helped us have deeper insight with respect to various of these effects, home field advantage by park, et cetera, et cetera. Okay, so that's that. That's kind of the way I've tended to approach these sorts of problems, and hopefully I've made my case that it's a rewarding way of looking at these complex set of problems, or maybe it's just the way that I'm predisposed to do it. But actually, it's it's not obviously not the only, obviously not the simplest, and not necessarily the best approach to any one of these problems. And I don't want to leave you guys let you guys. I want to make sure you guys realize that various other methods have been applied to various of these problems, in particular player and game evaluation. Random forest tree type approaches, nearest neighbor type methods, regression techniques, other collaborative techniques, more traditional Bayesian statistical models. If you're paying close attention, and if you're a statistician, you would realize that kind of the way I've done things is some sort of bastardization Bayesian / frequentist approach that a lot of statisticians give me crap about, but I'm not a statistician, so I don't have to listen to them. And various heuristic methods, and some of these with very strong results. It's certainly very easier in a lot of respects to throw in a bunch of other variables into a random forest that's trying to evaluate who's going to win a game, and kind of try to capture a lot more information a lot more quickly. But at the same time, sometimes some of the best approaches of trying to use random forest to predict who's going to win a game, they'll use outputs of models like our model of player ability as an input into that model to get the best outcome. Because the more you know about how good the underlying players actually are, that can certainly help you get better outcomes with respect to some of the other techniques. And then on the flip side, the way our system works, the way we've built it, we can also sometimes and do incorporate various other techniques into various components of of what we're doing. For instance, with respect to how we model plate appearances, how we model substitution heuristics, where we can, at times incorporate some of these other, can and do incorporate some other techniques into helping us, kind of improve that system as well. I also don't want to leave you guys to think, and I think we've already talked about some of this. So obviously, the models I presented here aren't perfect, best possible models with respect to these problems. So there's lots of potential improvements here. For instance, some improvements that we could make to the models I've mentioned. Some of these we've actually mentioned along the way, but better models for what this prior distribution looks like. Maybe we could use mixture models with hidden variables in terms of batters could be drawn rather than from one prior with kind of the single mode. Actually, a mixture model. We do in fact have a mixture model right now, determined from the top down, where we actually model position players as batters and then we model pitchers as batters. So we have two different prior distributions, but maybe it's a lot more nuanced than that. Maybe there's kind of these multimodal mixture models with these hidden variables. As we discussed earlier, pitch level analysis, there's really, felt like when I started this analysis, the play level analysis was very granular, but you can go deeper to the pitch level analysis, and especially, incorporating richer data, that can make a lot more sense. And also, the 14 abilities, we generated, were completely arbitrary, really. So that's not to say you couldn't improve on that. And also, this sort of modeling, can be extended, very well actually to other sports. We've actually discussed how we do it a little bit. Discussed football, and we've built, more rudimentary models of basketball. But it's not unreasonable. A lot of people ask me, well, basketball and soccer, these sorts of sports, they must be that much harder because they're not these discrete, obvious state space problems. And in one sense, yes, it might be harder to build more granular models now, but there's still, there's still a state space. Basketball stops and starts all the time. And like we said, this player tracking data, or this tracking data of players and balls and whatnot, this is coming. It's already here in baseball and basketball and soccer, and it's not here in other sports. It's coming, and I do believe that, eventually we'll be able to get our hands on it, even if the teams don't want to open it up now. And then there's a lot you can do with this tracking data. So I wanted to kind of quickly, introduce those of you that aren't that familiar with it to kind of what this data looks like with respect to baseball. So any of you guys that follow baseball at all, especially if you follow it online, are probably familiar with the pitch FX data and generally what it is. Basically for every pitch now for the last few years, MLB's been releasing the release point of the pitch, the exact point the pitch crossed the plate, the velocity of the pitch, the break on the pitch. Someone somewhere adds something called like a nasty index or something. I don't know what that is, but basically, for the most part, all you would want to know about a pitch. And for the last couple of years, they've also been gathering this hit data, which it was, astutely pointed out, we as the general public don't currently have access to it. The teams have access to it, and I'm pretty convinced that very few of them know what to do with it. So now, not just watching what happens when the ball's coming this way, but now we're measuring what happens when the ball's going that way, the speed of the ball, the launch angle, the distance, the hang time, all of that, at the exact, place that it landed. We're now gathering that. And just this year, they've started experimenting with now the field FX, the last piece of this, holy trinity of tracking data. So now, at least in a couple parts, they're tracking exactly where the fielders are when the ball's hit. How long it takes them to take their first step. What direction they move. Where they are when the ball's caught, if they catch the ball. Et cetera, et cetera. And like I mentioned, there's similar data being generated in basketball and soccer that's tracking where the ball is, where all the players are, every pass, where, all the significant movements. They're actually, allowing for much deeper analyses in those sports. So that's, the first, kind of use for this new data in my mind is, well, okay, we can create these more nuanced states in the fluid sports like basketball and soccer. So we have a model, with respect to basketball, but it's a very primitive model. It analyzes, okay, a team got the ball, they had these 5 guys on the floor. This is the guy that shot the ball, this is the guy that rebounded the ball, or went in, you state, et cetera. It's very simple, but now you can actually create, as fluid a model as you want. You can, in theory, kind of the holy grail of this sort of data would be able to prescribe a value to the location of the ball and all 10 players at any point in time. So we have the ball, this pass is made. How did that change the value? What's the risk associated with making that pass in terms of the probability it's going to be a turnover, et cetera, et cetera. Model that out, be able to evaluate those decisions, evaluate the whole game in a much richer way. And likewise, certainly with respect to soccer, I mean, the World Cup's on right now, so it's all soccer all the time. The same sort of stuff. That's what people want to do with respect to the soccer data as well. Is come up with that value and really get deeper insight, especially since relative to the more American sports, there's not that much data that people have been doing that much with historically. People have been doing a lot because soccer is very popular. But certainly the people I know that have done a lot more soccer analysis than me, they still feel like they've been grasping and they've been held behind, and now they've got all this player tracking data, and now they don't know what the hell to do with it. But even with respect to baseball and other sports, we can still build much richer models. Like I mentioned earlier, this ability space, these 14 outcomes. We don't have to look at modeling, a player in the sense of what his outcomes are. We can now model a player in the sense of if he sees this particular type of pitch on this count, this is the distribution of where the ball's likely to go, if he decides to swing, and this is the probability he's going to swing and all that stuff. And it certainly gives us the potential to get, these much richer models with respect to how good players are, what's likely to happen in the games, but also these much richer, decision and even game theoretic models with respect to decisions batters and pitchers are making, the positioning of the players in the field. Certainly in baseball, in the last year or two, teams have been doing a lot with player positioning, just looking at, I think kind of these more precise hit charts. But there's still, a lot deeper analysis you could do in those realms as well. So this is my last slide. I just wanted to spend a couple minutes talking about fantasy sports. Now the whole talk up till now, especially kind of the optimization, the decision analysis components of it, have really been geared around the decisions that teams make and how to optimize with respect to those. And that stuff's interesting, and that's what I got my thesis off of. But there are 30 Major League Baseball teams, and there are millions of fantasy baseball players, and there are tens of millions of fantasy football players, and there are 100 million people that fill out March Madness brackets every year. So this fantasy sports market is, in fact, by far the biggest market for sports analytics right now. And these people are hungry for analysis and tools, in large part because fantasy sports in this country is really the legalized outlet for sports gambling, since traditional sports gambling is illegal. And the other reason I wanted to talk about this is because it's actually the most promising current application of all the sports research I've done. We've actually, applied the research, a lot more in fantasy areas as opposed to, I've met with teams, I've collaborated with players from teams, I've given them access to a lot of research and data, but then that's kind of a black hole. There's a lot more fantasy sports players and outlets that we've kind of worked with and that have gotten our data out. As Todd mentioned at the beginning, actually, the first product we launched in this area, my partner Gaurav and I have a website, bracketvoodoo.com, a March Madness optimization engine, which helps people optimize their March Madness brackets. At one point, I considered giving you guys a demo, but A, I've been talking long enough, and B, I realized that people only care about March Madness in March. So next March, we'll talk again. But and actually, like all the research, all the modeling I've discussed thus far, actually, it's a good starting point for analysis and optimization with respect to these applications. So the fact that we're able to generate these predictions of game outcomes, projections of player outcomes with this full distribution of what the player is likely to do, his probability of hitting a home run, his probability of hitting 2 home runs, all that sort of stuff. That's a good starting point for this analysis. Then we just extend those models to incorporate the behavior of other fantasy players. So for instance, in your fantasy baseball matchup, we know your opponent, we know what lineup he's likely to play. Then we can model out all the games and look at the distribution, your probability of beating that opponent if you field a certain lineup. And then we can analyze, how that probability changes with different lineups. And for instance, if you're the underdog in that matchup, maybe we can push you towards players with the higher variance, higher upside. The guy that's probably not going to do that well, but there's a decent chance he's going to hit there's a chance he's going to hit that home run or that 2 home runs, the power hitter, the Adam Dunn, if you will, that you need to be playing versus those people. So that's what these sorts of solutions are geared towards. Supporting individual fantasy decisions, optimize your lineups and brackets, help you evaluate and maximize your chances of winning. And along the way, we started generating additional insights. So the way we set up these models, we can actually update and evaluate, in real time, give you, real-time updates of your probability of winning this matchup, identify the key games, identify the key matchups, that if this player does this good, how's that change your conditional probability of winning, et cetera, et cetera. And one other thing that's really attractive about this application, the applications for baseball teams, it's great when you can optimize, with respect to, optimal bunting or intentional walks and help a team get, an expected value of 1.5 wins a year, and that's worth a lot in baseball. But in fantasy, like in March Madness, you can optimize someone's March Madness bracket and multiply their probability of winning that pool by 2 to 10x. Or in fantasy sports, you can really get a big impact when you're dealing with these sorts of applications, especially compared to optimizing on-field decisions and even optimizing traditional gambling decisions versus the gambling line. So that's that. Thanks again for having me. Like I said, I cover about 1% of what sports analytics is, and I'm happy to follow up with you guys on any of this or any other applications if you want to follow up here or email me later. Certainly right now we can take a few questions. Yeah.
Love your presentation. There's a lot of good information. I'm a huge fantasy sports player, so I'll talk more about that later. In terms of like March Madness, how accurate were you to the last one?
As accurate as anybody else, but not very accurate. That's the biggest challenge of a March Madness tool is I can give you a 10x chance of winning your pool, right? You're in a pool with 1,000 people, so I took your chance of winning from 0.1% to 1%, and you should think that's awesome, and you should just give me $50. But there's a 99% chance that you're going to come back pissed off at me and tell me I'm an idiot. That's part of the problem. I mean, our underlying predictions, we didn't think either of those teams were going to be in the final, and that's where this much bigger edge that I talked about that you get in March Madness, for instance, it's not from us predicting who's going to win much better than everybody else and saying, oh, we're the ones that know Connecticut's going to win, but it's saying we're the ones that know that if you're playing against 1,000 other people, don't pick Florida and don't pick Louisville and don't pick Arizona. Actually, you should pick one of these 3 or 4 or 5 other teams. So we did have a few people that, and we were kind of since we were optimizing for every person for their bracket, we didn't have as many people. We had a couple of our users that were picking Connecticut and Kentucky. We had a few more that were kind of along Wisconsin in some of these larger pools. That one didn't break our way as well. But I mean that's the thing, especially with March Madness. It's still one tournament. There's still a lot of variance. Yeah.
And what software package do you use for the analysis and the data storage for Bracket Voodoo and for your prior work?
I'll let you, when we get into data storage and the product stuff, I'll definitely let you talk to my partner Gaurav later. The initial analysis, my default is generally MATLAB for kind of the prototyping and the initial analysis. Then in terms of like Bracket Voodoo turning these things into a product, we take some of that stuff. We're actually using some open source, some Octave, in production now, and the stuff we're building out right now, or we just rewrite those algorithms in JavaScript or whatever else. The data storage, I know we're using Mongo and AWS, and I don't know. We have some CSV. We still have some CSV files. Don't look behind the curtain. We're still, some things are still in a beta phase for sure. Okay. Yeah.
This is about your priors. What caused you to choose beta and not maybe uniform, for instance?
And not uniform?
Because you don't really know what the priors are.
Well, you mean a uniform prior in terms of the underlying abilities of players to walk uniform, or you're talking about,
So each player is given
no
information, right?
Right.
So each player is equally likely to do that.
Right. Right. Well, I mean, the uniform, like the uniform distribution does, generalize the beta 1-1 or whatever is the uniform distribution, right? So our maximum likelihood method could have picked uniform if it wanted to. It never did. I mean, it did some weird things in the edge cases. We certainly had data sets where, like, what's the best prior for ground ball home runs? And it's like, well, nobody's done that in 3 years, so I don't really know what to tell you. But, we had to fudge around the edge cases like that. But we started with what I thought was a flexible setup of trying to fit a beta distribution, and then we let maximum likelihood fit it, and then we analyzed the models after the fact, and we decided they looked pretty good. So that's kind of modeling 101 the way I do it. I'm always happy to hear ideas from you guys too. So happy to talk. Yeah.
What were some of the higher impact discoveries in the baseball modeling realm? You mentioned, of course, the interesting part about using more rookies is a high impact thing. What were some other high impact strategies in terms of as they might translate into expected wins over the course of the season or so?
Well, one of the ones that I kind of glossed over a little bit was with respect to this optimal bunting. Our analysis, and this is actually a topic that's kind of come back around in the last few months, especially with these radical shifts. And our analysis was saying, well, teams should bunt a lot more. We should experiment. Everybody should be bunting a little bit to see how good they are. We've got this upside. I mean, maybe they figure this out in practice that they're no good at bunting. But I don't know. It certainly seemed, from our analysis, that people that actually tried to bunt in a lot of situations, a lot of good things happen. And once you can actually account for the defensive shifts, there's even that much more of a reason why you should be bunting. And there's some anecdotal evidence. Some of these big sluggers have started trying to bunt, and more often than not with disastrous effects, I think, lately. But still, I think even those guys, I mean, they bunted twice and it didn't work out. I mean, keep trying. So that was kind of one of the things, and that's one of the issues that also makes it a little hard to measure how much impact this could have, because optimal bunting is very much a game theoretic scenario. But it really depends on where the defense is going to be. So our optimized model right now might say all 9 of these guys should try some bunting. But once they do that, once the guys start having success, then the defense is going to react. Then you have to be able to account for that. And it's really this field FX data is without data like that, we've got somewhat crude ways of trying to deal with that. But if we had access to this data, then we could actually build much more powerful models around that. Yeah.
Did you test your models? You said they came close to the lines for gambling. Like, how close? Like, if you were putting money on it, how much would you have lost?
It's a good question, and there's still. And even though in baseball there's 2,400 games in the year, and the gambling lines do have that spread, and our models would still say that you should bet on a few hundred games a year, and on average we looked at that over a series of years, and I think over the course of 3 years, we would come out slightly ahead. But there's still a lot of variance, and that combined with the fact that I don't want to move to Nevada, kind of led us at this point when we really went down the last mile that fantasy and especially like daily fantasy is a much more attractive option because we can play a lot more games and it's quasi-legal. We think it's legal. Everybody says it's legal for now. But so it's actually been a much more attractive outlet. I do know a few people that are more into traditional gambling and build those models and syndicate things and whatnot. And we've shared a little bit of data with those guys, but I mean, really, it's all fantasy and daily fantasy nowadays, I think. Yeah.
Two of them, both real quick. So with the decision making, did you find yourself like evaluating like Bill Belichick? He really is a god, and someone else is just terrible. And then the second one with all the field effects and pitching, doesn't like the calibration of the data collection become much more important? And if you're kind of building your models where, the reader went out at Candlestick, or it's not called Candlestick, or AT&T, if that goes out, then your whole system falls apart.
I mean, as far as starting with the second question first about dealing with the pitch effects and hit effects data, I mean, I haven't, as was mentioned, the hit effect stuff's still proprietary. I only know about it. I haven't actually worked with the corpus of it. And honestly, the pitch effects data I haven't done that much with yet. I mean, your example about, the data goes out, what do we do? I mean, certainly the modeling component of it, we can deal with missing data. That's not going to screw everything up. Now, if we're applying this stuff real time and trying to, to learn things and apply models real time, that might cause us some issues, and we'd want to have backup models. So it would be good that we spent 5 years building these models, I guess. But once we have the new models, we want to throw all this stuff away. Does that at all answer that? My take on that question. Your first question about do I have a take on is Bill Belichick a god, and then there's everyone else. I mean, the interesting story about Bill Belichick, he's, at least in recent years, had, kind of this most famous go for it on 4th down play against Peyton Manning and the Colts. It was the Colts, right? Yeah. But what's funny about that is that, that was a bad idea. I mean, Bill Belichick, that whole little aside about, coaches don't go for it because, A, they probably don't realize that it's a good idea, and B, if they did, they'd, probably be scared shitless. I do believe that Bill Belichick might be just about the only NFL coach that wouldn't be subject to be there. And I think he's further ahead on A, but I think Bill Belichick's a great coach, just like, I mean, there's no denying his success, but he's certainly, he's got a lot of job security. He can do whatever he wants to do, and some of those things he's done are questionable. Now, I mean, getting back, I guess, to your root question, I haven't actually analyzed every decision made by every NFL coach, so I don't have a rating of the coaches.
Okay.
I just have, colorful things to say, or off colorful things. Anyway. Yeah.
Did you use the H factor to tease out who might be confusing?
The what?
So the fact about the H factor, did you look at outliers from the possible juices?
Oh, the juicer model. That's one of those things that's way up near the top of the list of analyses I always wanted to do, but haven't gotten around to. I do know for a fact that that juicing in that era screwed up a lot of people's age effect models for a long time. And but I never have sat down and looked at the outliers with respect to that who are the most likely candidates. I think the biggest examples are painfully obvious to everyone, and it's interesting, especially kind of in more recent years when we've seen kind of the Chris Davis going off, or Raul Ibanez had like crazy like 2/3 of a year a couple years ago or something. And invariably some blogger somewhere kind of raises the question, and invariably they get knocked down. And I would certainly, if I had been more on top of my stuff, then would have just as likely been that blogger. And tried to back it up. Well, here's the probability based on the model, that these guys are juicing. But then again, to answer your question, I haven't actually looked at that. No, that's what the last question. But, yeah.
Do you take into account like roster changes, like players getting sent down, and also like September, expanded rosters?
In what aspect?
In your season, simulations.
Yeah, we definitely take into account who's on the roster when we're
players and hot prospects, each players.
Yeah, we definitely take that into account. Now that's certainly there's every level of this sort of approach. Obviously, that's the biggest kind of cost of this sort of approach. I mean, it takes a lot more time than if you're modeling one specific question, throwing something into a well understood type of model. But when we extend the model into the season level, which I didn't really spend that much time on, then there's a whole other level of considerations you want to take into in terms of probability players get injured. Ideally you take into probability players are going to be traded and drop down and called up. And we still have there's definitely room for improvement in our models with that respect. What we certainly do, especially when we're modeling a specific game, take into account exactly who's on the roster, who's on the bench, their likelihood of coming into the game, etc. Yeah.
Any places to go to get like basketball player tracking data?
So the sport view data, at least in some manifestations of it, I know are available. I haven't been digging. You can get it through the NBA's website. You can see the data I've seen is still somewhat aggregated, either on a game level or kind of running sport view data. But those sort of like advanced stats that you're seeing, that you see that when people are looking at shot charts and hit and miss and when they're analyzing the more advanced data, you can actually go look at kind of like the sport view box scores for games and see most of kind of the underlying data that the people that are doing that analysis on are looking at. I certainly want to get the granular data, the play-by-play data, and I don't yet know how to get access to that short of going through a team, because I think actually at this point I think the NBA owns it, so I don't know like right now if you can. I do know some people in a couple teams that I've talked to a little bit about, but haven't gotten to the level of trying to get them to let me look at it or figure out what I'll have to give up once they do. I have gotten some people to let me see some of the soccer data, but still haven't done that much with it yet.
So I think Brad's going to stick around after this for a little bit.
Yeah.
More questions?
Yeah, sure.
Let's thank him.